Hello, my name is Scott Swartz, Chief Technology Officer of Nexceris and the Principal Investigator for this project. Thank you for watching our video. This Phase 2 ARPA-E project is a collaboration among 3 dynamic technology companies, Nexceris, Czero, and Brayton Energy. We aim to design, build, and demonstrate a highly efficient 100 kilowatt scale hybrid power system based on a solid oxide stack and a gas turbine. In the first phase of this project, we established a pressure-tolerant 10 kilowatt scale stack design, which provides the primary focus for Nexceris work in Phase 2. The system we are building will include multiple 10 kilowatt scale stacks of our Phase 1 design. Thus, Nexceris will be scaling up cell and stack production to meet the needs of system builds at Czero in the second project year. Nexceris also will be collaborating with the National Energy Technology Laboratory on pressurized testing of full-scale stacks, leveraging a unique facility that NETL is currently building. Czero is leading system design and modeling work and controls development work. They currently are building a system model to inform specifications of balance of plant components and to define the control strategy. Brayton Energy is contributing their previous experience in SOC turbine hybrid system development, along with their gas turbine, combustor, and heat exchanger technologies. The second year of the project will involve system construction and validation testing, and the project will culminate with an exciting demonstration of the hybrid system. Now I'd like to let Gene Arkenberg talk through the work at Nexceris on SOC stack technology.
Thank you, Scott. I'm Gene Arkenberg. I'm the Director of Stack and Systems Technology at Nexceris, and this is the update for our accomplishments to date from the Phase 1 project and going into the Phase 2. So far, we developed a COMSOL model to predict the optimal catalyst loading to balance the thermal gradients from internal reforming within our cells in the stack that we're looking at using on the system. We also leveraged our design and manufacturing flexibility to establish 2 platforms, a full-scale one, which we could use for the system, and a half-scale one for de-risking design attributes of the stack technology before executing the full-scale stacks. An example of our ability to scale is shown in the top right 2 pictures from one of our smallest stacks, which is just under 500 watts, to a 2.2 kilowatt, which is the half-scale stack we mentioned. And then on the far right on the top is the actual full-scale stack platform at a 1.8 kilowatt scale level. So this is not the full level, but a portion as we're validating it. In addition to that, we have developed and implemented improved sealing materials to help for operators with the pressurized stack operation. And then ultimately, we validated the performance of the large scale stack and the half scale designs to our equivalent standard performance as shown in the bottom right-hand corner.
And now I'd like to have Mike Sprengel from Czero talk about his hybrid system design.
Thanks, Scott. My name is Mike Sprengel. I'm a senior analyst here at Czero and leading up the modeling and architecture design effort for Czero's side. So in order to achieve our goal of ultra-high fuel to electrical conversion efficiency, we're tightly integrating a solid oxide fuel cell and a gas turbine into an integrated system that's more efficient than either of these systems could be on their own. To that end, at the conclusion of this project, we will build and demonstrate a 100 kilowatt system capable of achieving 70% target efficiency when operating on natural gas. On the right, you can see a high-level schematic of the system where we have the turbomachinery's compressor supplying compressed air to the cathode side of the stack, and then we're supplying natural gas to the anode side. The stack is capable of converting this fuel into electricity at a very high efficiency. We're operating the stack around 850 C and pressurized between 3 to 4 bar. Running the stack pressurized compared to ambient allows us to increase the efficiency. Now, this system, like any other SOC, always has some amount of unused fuel at the anode outlet. We're taking this unused fuel, combining it with the waste stream from the cathode, which is already pressurized and hot, combusting it in the combustor, and expanding it through the turbine. We're able to recover enough power from this waste gas stream to power the compressor and have enough left over to produce electricity in the generator. We combine this electricity in the generator with the electricity produced by the stack and the power electronics and export it to the grid, creating a very high efficiency system. So as part of our development efforts, we have created a high fidelity dynamic plant model of the integrated SOFC GT system and validated the subsystems. We are currently using this plant model to support our architecture design and component sizing efforts, allowing us to optimize both the system architecture and the component sizing for performance and efficiency, while also accelerating our pace of development and reducing our technical risk. This same plant model will be used to develop and validate our control strategies, which are expected to be quite complex through model in the loop and software in the loop techniques, and will likely also be used as part of a model-based control strategy. Thanks, Scott.
Hey, Tom, can you talk about some of our technology to market activities on the project?
Sure, Scott. Thank you. I'd be glad to. I'm Tom Harvey, Product Development Manager at Nexceris, and we're going to talk a little bit about the market applications. The hybrid power generation system being developed by this team will provide power to a variety of applications across a diverse set of industries. Maritime, freight and passenger rail, and trucking industries can benefit from the low emissions and high efficiency of the system. Stationary power users, either grid-connected or standalone, can also benefit from the improved resilience, sustainability, and energy independence. The system can allow EV charging stations to be placed in locations with natural gas but limited electrical power. Efficiency improvements of up to 9 percentage points over existing SOFC gas turbine hybrids are planned. And combined heat and power applications can provide significantly higher efficiencies. Back to you, Scott.
Kyle, why don't you talk a little bit about Nexceris?
Sure, Scott. Hi, I'm Kyle Shen. I'm President and CEO of Nexceris. Nexceris is a clean energy company that makes fuel cells, batteries, and sensors. We were started in 1994, and our tagline is where energy meets the environment. Nexceris's vision is to create a better world through energy innovations. We do that by collaborating with leading companies around the world to transform our ideas into solutions that make energy production safer, more efficient, and environmentally responsible. We've partnered with some of the largest companies in the world, including Honeywell, two of the largest automakers in the world,